Long before silicon chips and neural networks, humanity dreamed of creating life from lifeless matter. We carved wooden automatons, built mechanical calculators, and wondered, could we one day create something that truly thinks? This is the story of artificial intelligence, a tale of ambition, innovation, and the audacious quest to replicate the human mind. The seeds were planted centuries ago. In ancient Greece, philosophers pondered the nature of thought itself. Could reasoning be reduced to mechanical rules? Could logic be formalized? These weren't idle questions, they were the foundation upon which artificial intelligence would eventually be built. In 1770, a Hungarian inventor named Wolfgang von Kempelen unveiled something extraordinary, the Mechanical Turk, a chess-playing automaton that defeated some of the greatest minds in Europe. Dressed in exotic robes and seated behind an ornate cabinet, this machine appeared to think, to strategize, to compete. Of course, it was an illusion, a human chess master hidden inside. But the Turk represented something profound, humanity's fascination with intelligent machines. Even as a hoax, it asked a legitimate question, could a machine truly think? And if so, how would we know? Jump forward to 1843. Ada Lovelace, daughter of the poet Lord Byron, was collaborating with inventor Charles Babbage on his analytical engine, a mechanical computer that was never fully built but was revolutionary in concept. While Babbage envisioned a calculating machine, Lovelace saw something more. In her notes, she wrote that the analytical engine could manipulate symbols according to rules, and might one day compose music or produce art. She imagined a machine that could go beyond mere calculation. Many consider her the world's first computer programmer, and a prophet of artificial intelligence. But Lovelace also understood the limitations. She wrote that machines could never originate anything, they could only do what we know how to order them to perform. This tension between potential and limitation would echo through the next century of AI development. The modern story of artificial intelligence truly begins with one man, Alan Turing. During World War II, this British mathematician helped crack the Nazi Enigma code, potentially shortening the war by years. But Turing's contributions went far beyond cryptography. In 1936, Turing published a paper that laid the theoretical foundation for all modern computers. He described a simple machine, now called a Turing machine, that could perform any computation that could be described by an algorithm. This wasn't just mathematics, it was philosophy. Turing was defining the boundaries of what could be computed. Then, in 1950, Turing published a paper titled Computing Machinery and Intelligence. It opened with a bold question, can machines think? Rather than answer directly, Turing proposed a test. If a machine could convince a human interrogator that it was human through conversation alone, then for all practical purposes, it was intelligent. This imitation game, now known as the Turing test, remains one of the most influential ideas in artificial intelligence. Summer, 1956. Dartmouth College, New Hampshire. A group of brilliant minds gathered for an 8-week workshop that would change history. John McCarthy, Marvin Minsky, Claude Shannon, and Nathan Rochester organized what they called the Dartmouth Summer Research Project on Artificial Intelligence. This was the moment artificial intelligence received its name. The organizers believed that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. Their optimism was infectious. They predicted that significant progress would be made in just a few months. They were wrong about the timeline, but right about the importance. The Dartmouth Conference established AI as a legitimate field of study. It brought together the pioneers who would shape the discipline for decades to come. The age of artificial intelligence had officially begun. The late 1950s and 1960s were a time of remarkable optimism. Computers were solving algebra problems, proving mathematical theorems, and even speaking English. In 1966, Joseph Weizenbaum created ELIZA, a program that could conduct conversations that seemed remarkably human-like. ELIZA worked by pattern matching and substitution. It was essentially a clever trick, yet people formed emotional attachments to it. Weizenbaum's own secretary asked him to leave the room so she could have privacy while talking to Eliza. The program revealed something profound about human nature: we're predisposed to perceive intelligence, even when it's not truly there. But by the early 1970s, reality set in. The problems AI researchers faced were far harder than anyone imagined. Computers could prove theorems but couldn't recognize a simple face. They could follow rules but couldn't understand context. Funding dried up. Interest waned. This period became known as the first AI winter. The field had hit a wall. Symbolic AI, the approach that dominated early research, relied on explicitly programming knowledge and rules. But the world was too complex, too messy. How do you teach a computer common sense? How do you encode the nuances of human language? These questions seemed insurmountable. In the 1980s, AI experienced a renaissance. The key was narrowing ambitions. Instead of trying to create general intelligence, researchers focused on specific domains. These expert systems captured the knowledge of human specialists in fields like medicine, chemistry, and engineering. Mycin, developed at Stanford, could diagnose bacterial infections and recommend treatments as well as expert physicians. Exion, used by Digital Equipment Corporation, configured computer systems, saving the company millions. For a brief moment, it seemed AI was finally delivering on its promises. Companies invested billions. AI startups proliferated. But once again, limitations emerged. Expert systems were brittle. They couldn't learn from experience or adapt to new situations. They required constant maintenance. And building them was expensive and time-consuming. By the late 1980s, the market collapsed. The second AI winter had arrived. While symbolic AI struggled, a different approach was quietly gaining momentum. Neural networks, inspired by the structure of the human brain, had been proposed as early as the 1940s. But they required enormous computational power and vast amounts of data, neither of which was readily available. In 1986, Geoffrey Hinton and his colleagues developed a technique called backpropagation, allowing neural networks to learn from their mistakes. Still, neural networks remained on the fringes of AI research for years. The breakthrough would require waiting for technology to catch up with theory. That moment came in the 21st century. Computer processors became exponentially more powerful. The internet generated unprecedented amounts of data. And researchers discovered that deeper networks with many layers, could learn incredibly complex patterns. Deep learning was born. In 2012, a deep learning system called AlexNet won the ImageNet competition by a stunning margin, revolutionizing computer vision overnight. Suddenly, computers could recognize objects in photographs better than many humans. The decades-long dream of machine perception was becoming reality. The 2010s witnessed an explosion of AI capabilities. Virtual assistants like Siri and Alexa brought AI into our homes. Recommendation algorithms shaped what we watched, read, and bought. Self-driving cars began navigating real streets. AI was no longer confined to laboratories, it was everywhere. In 2016, DeepMind's AlphaGo defeated Lee Sedol, one of the world's greatest Go players. Go, an ancient game with more possible positions than atoms in the universe, was thought to be decades beyond AI's reach. Yet AlphaGo didn't just win, it played moves that human experts called beautiful, creative, even intuitive. Then came the language models. Systems that could write coherently, translate languages, summarize documents, and even generate computer code. These weren't following hand-coded rules, they were learning patterns from billions of words of text, developing their own internal representations of language and meaning. By 2023, AI systems could create photorealistic images from text descriptions, compose music, and engage in conversations that were often indistinguishable from human dialogue. The Turing test, once thought to be decades away, was being passed with increasing frequency. But how does it actually work? At its core, modern AI is about pattern recognition on an enormous scale. A neural network is a mathematical function with millions or even billions of parameters, numbers that get adjusted during training. During training, the network is shown countless examples. For image recognition, millions of labeled photos. For language models, vast corpora of text. Each time the network makes a mistake, its parameters are adjusted slightly. Gradually, through this process of trial and error on an industrial scale, the network learns to recognize patterns too subtle and complex for explicit programming. The remarkable thing is that we don't fully understand what's happening inside these networks. They develop their own internal representations of concepts, their own way of organizing information. In a sense, they're black boxes. We know they work, but we can't always explain why they make specific decisions. Today, artificial intelligence stands at a crossroads. The promises are extraordinary. AI could revolutionize medicine, discovering new drugs and diagnosing diseases earlier. It could help solve climate change by optimizing energy systems. It could unlock scientific discoveries by recognizing patterns invisible to human researchers. But the perils are equally significant. AI systems can perpetuate and amplify human biases, discriminating in hiring, lending, and criminal justice. Deepfakes can create convincing but entirely fabricated videos, threatening truth itself. Autonomous weapons could make decisions about life and death without human intervention. There's also the question of economic disruption. As AI systems become more capable, what happens to human workers? Some experts predict widespread unemployment, others foresee a world where AI handles routine tasks while humans focus on creative and strategic work. The truth likely lies somewhere between these extremes. And then there's the existential question: what happens if we succeed in creating artificial general intelligence, AI that matches or exceeds human capability across all domains? Would such a system be our greatest tool or our final invention? These aren't science fiction questions anymore. They're being seriously debated by researchers, ethicists, and policymakers around the world. Throughout this journey, one truth remains constant: artificial intelligence is fundamentally a human creation. Every algorithm, every training dataset, every design decision reflects human choices, human values, and human biases. The researchers training these systems come from specific cultures and backgrounds. The data they use reflects particular perspectives and histories. Even the questions we choose to pursue with AI, which problems we deem worthy of solving, reveal what we value as a society. This means the future of AI isn't predetermined. We're not passive observers of an inevitable technological trajectory. Every day, people are making choices about how AI is developed, deployed, and governed. These choices will shape whether AI becomes a force for human flourishing or a source of harm and inequality. The creation of artificial intelligence is not a single moment, not a lightning bolt of inspiration or a triumphant unveiling. It's an ongoing process, a dialogue between human ingenuity and computational possibility that has stretched across centuries and continues into an uncertain future. From Ada Lovelace's vision to Alan Turing's test, from the optimism of Dartmouth to the bitter AI winters, from neural networks to deep learning, each step has brought us closer to understanding both artificial and human intelligence. And perhaps that's the greatest gift AI offers, not just powerful tools, but a mirror reflecting back our own minds, challenging us to understand ourselves more deeply. The story of AI is ultimately a story about us, our creativity, our ambition, our fears, and our hopes. We dreamed of creating intelligence, and in doing so, we're still discovering what intelligence truly means. The creation continues. The questions multiply.